I'm going to tell you about an obsession I've had for quite some time. And it actually started when a colleague of ours, Stergios, came back from a conference on such polynuclear transition metal clusters, where he had heard a foreign colleague say that high temperature expansions are not for chemists. High temperature expansions is a technique which is usually invoked when molecules get big or things get complicated. And I will not go so much into it, but it was kind of a provocation. So I thought of making this something which is useful also for chemists. And in order for this not to become a completely erratic message without focus, I should say what this is all about. We will talk about J values for the next 25 minutes. And a J value is a parameter which is multiplying this dot product of spin vectors or of angular momenta vectors. And just to repeat a thing which cannot be said too often, the spin is a vector property, and the interaction between two vectors can only become useful in this context by taking a dot product, which is a scalar. See, if two small spins, each of quantum number 1/2, are interacting, where the interaction is described by this operator, it results in spin states having spin values of 0 and 1. And if this parameter is negative, the triplet, the S = 1, is the ground state. Or if this parameter is positive, the singlet is the ground state. And we are also going to talk about magnetizations or magnetic susceptibilities. And when computing this property, each and every level contributes to this property. And so the contribution from each level is that it needs to have a derivative in a magnetic field in order to be active, and it becomes temperature dependent because the population of each level is temperature dependent. See, with certain approximations, you don't need to sum over every energy microstate, but you can sum over all the different total spin values being present. And so for a given energy level diagram, for instance, presented here as a sum of delta functions, you get curves which could look like the ones you see to the right in the figure. And these curves are, so to speak, a little boring because they are always positive. They become proportional to 1/t for high temperatures. They are finite at temperatures equal 0, and they might have some features like minima and maxima between temperature 0 and infinity. And actually, if you are able to compute an energy level diagram presented here to the right, it is absolutely correct to use this energy level diagram and put this as input into this formula, and you get a susceptibility curve. But hang on, if you look at the energy level diagram to the right, why, for instance, should that yellow energy level diagram, energy level, be more interesting than the orange one? It cannot be true that all this is necessary for producing a curve which is essentially without any spectacular features. And what I'm going to talk about now is how far is it possible to replace this energy level diagram you see on the top with one which is very much simpler, like some of these stick diagrams, or some of a handful of delta functions, and produce essentially the same curve. And we start to introduce the necessary quantities. We start very simple. See, if you have a spin system composed of two spins, each of spin quantum number 5/2, you have a system which has matrix dimensions 36. The Heisenberg operator here with J positive results produces an energy level diagram shown to the left. And the spin multiplicities range from 0 up to 5. The 0 is the ground state, 5 is the highest energy state, and they are separated by a so-called Landé interval, so to speak, that the energy separation gradually increases upwards here to the left. These states, they have degeneracies, and they are given very simply by 2s plus 1. So here at the top there are 11 microstates, and at the bottom there's 1 microstate. These levels, they also have expectation values, and essentially an expectation value for sz square, which is a necessary input for the formula from before. Another system, like being composed of 4 manganese trees, now each center has spin 2, and this results in a matrix dimension of 625. And the bottom of the energy level diagram is given at here below. And you see already now the systematics of spin multiplicities increasing upwards is violated. There is an s equals 0 at the ground state, then comes 1 and 2, and then again comes from s equal 1, and then 3, and then it increases further up. And so this system here has spin multiplicities ranging from 0 to 8, and there are 12 s equal 1s, and there are 15 s equal 4, and they are kind of distributed not entirely randomly, but it's not easy to predict their order. Going a little bit further up in complexity, if you make a ring of 8 chromiums, each with a spin 3/2, you end up with matrix dimensions of 65,000. And an energy level diagram for this is shown here. It's actually provided to me by Stegios, who made an art out of computing energy levels for big spin systems. And a different way of showing what is going on in this mess of states is to compute the energies, or show the energies as a function of spin value. So the spin value is shown here at the bottom, and you can see that the spin singlets, s equal to 0, they extend actually the full energy range by and large, and the high spin multiplicities, they are mainly lying at the top of the energy range with an s equal 12 at the top. and an S equals 0 at the bottom. And here the number of spin multiplicities is given here. And essentially, it is not necessary here to diagonalize matrices of this size, because you can decompose that big matrix into blocks of size 1000, 1400, 1505, and so on. So this can still be dealt with using reasonably simple algorithms and formalisms. But see, here we can easily see that at the bottom, or here for all s equals zeros, the expectation value of sz squared is actually 0. And for the highest one, it has the highest expectation value of sz squared. And so in the energy range from here up to here, it must be expected that this expectation value in energy gradually varies from 0 up to this value here, which is around 50. And that's also an important quantity which we need in the following. And how do we extract this from that energy level diagram? Yeah, we can bin all the energies, and we can bin all these Fourier constants, also all the expectation values of a set, divide an histogram from here with that histogram, and we get how the expectation value of a set square varies with energy. So it varies from low, 0, up to a maximum at the maximum energy. Okay, so what comes now is inspired by 3 papers and monographs. They are given here. The uppermost one is completely from nuclear physics, and the second one is one trying to introduce the language of statistics to this type of energy level diagrams. And then there's a monograph in mathematics which has been very helpful for this. See, there is nothing stochastic with these energy levels, but the language of statistics comes in very handy. See, just to remind you, we are looking at an operator of this form. And if we take all the terms with J and exchange them with Latin letters, and take all the terms with B or SZ and exchange them with Greek letters, we need to be able to make the matrix representation of this operator and take it to some power n. If we do this, you can see there will be an awful number of terms, especially when n is 16. Then this ends up being a combinatorial nightmare. But this can be actually systematized. For instance, if you have a triangular connection in your molecule, then you can take all terms having this form, collect them into a so-called a graph or a pictogram, and compute how much this contributes to the trace or the moment of the energy level distribution. And what is this? You see, we are interested in these invariants, moments or traces of the Hamiltonian. We all know that the trace of a matrix is independent of the basis in which it has been created. But there are also other invariants, namely the sum of all energy level, all eigenvalues squared, all eigenvalues cubed, and so on. And these are also invariants. And these invariants are the important ones in the following. And how can we use them simply in the following? So here there are two kinds of determinants which are important, and they lead to orthogonal polynomials. They lead to a so-called, I don't know how this function should be called, I call it a window function. And from these polynomials, I can also compute the expectation value of SZ squared as a function of energy x. And some simple properties of these quantities are the following. The orthogonal polynomials, they have all simple roots, and our new eigenvalues will be the roots of these polynomials. These roots are also have a simple property. They are interlaced, meaning that the roots of the second order polynomial will lie in between the roots of the third order polynomials. And this is valid for all orders. And all the roots of this polynomial, they lie between the lowest energy and the highest energy. And if it is possible to generate these determinants up to a high enough order, then the roots of this polynomial are exactly the eigenvalues of the distribution. And this is actually all which is necessary. And now I will illustrate this with some examples to see how this proceeds. See, these determinants for a simple spin system, which we looked at before, they go as 36 up to, and at order 7, it collapses and becomes 0. It simply means that the system is completely solved at this order. And how does this proceed? Yeah, the first order polynomial has only one root at the center. The second has 2 roots, has 3 roots, 4 roots, 5 roots, and actually 6 roots from spin values 0 up to 5. And this is exactly the same exact energy level diagram for this simple dimer. And you see, in a sense, distribution-wise, it means that these distributions, they converge to the correct distribution. The same with the Curie constants. They also vary and end up being correct. And these Windows functions, they are shown here, and they have a very, very important significance. They say that also the maximum degeneracy which can be located at a single energy cannot be larger than this window function in order for the distribution to be consistent with the number of moments you have available. Okay, how does this now work for the energy variation of SZ squared? You see, from this system with the ring of 8 chromium ions, the density, the energy level diagram proceeds as this. And of course, the number of moments which can be calculated is limited. Also the computational burden in getting these moments is enormous, actually. But if we stop at order 8, we see that, we know all about the system, and that's why I'm comparing this formalism with something which is known already. We see that the outermost energy levels, they crawl towards the correct minimum value and towards the correct maximum value. And the window function actually provides an outer limit for where an energy level can lie. So actually, the lowest energy level lies between this blue cross and this histogram, and the uppermost energy level lies between that blue cross and this histogram. And if you use the orthogonal polynomials to compute the energy variation of SZ squared, you see actually it's the red line, which actually straddles all the points from that curve we computed before, from the correct ones. See at the bottom, I've also taken the highest order 8 energy level diagram and decorated it with this window function. And just to illustrate the significance of it, it says that the intensity here is 42. This 42 means that the maximum number of microstates which are outside this energy is at most 42. And if you count, remember we know all about this system, there is only an S equals 0, an S equal 1, and an S equal 2 outside this interval, and that amounts to 9 states. So this function here provides an important information about how many states we can expect to find, at most can find outside this the lowest histogram. Now we should use these the density of states at the bottom and the density of Curie constants to compute a susceptibility curve, and see actually already at order 1 we capture the maximum of the susceptibility curve, and increasing the orders it get even better. So yes, it is really possible to change the 65,000 energy levels to 8 energy levels with associated degeneracies to reproduce this relatively featureless curve. And just to finish this formalism, showing it once again, see in this field, this manganese 12 cluster has had a special position, and it's composed of a central core of 4 manganese 4s and has 8 manganese 3s around it. And if you make the bookkeeping, you find that there's a matrix dimension of 100 millions. And looking at the block sizes of the matrices here to the right, you know, it is not even worth beginning generating these matrices and diagonalizing them. First of all, they are hopelessly big. It takes really a lot of time to generate them, and you know, comforting facts, as they are Hermitian, it doesn't help anything, because the upper half contains so many numbers that it's useless. And which one of these energy levels should be more important than all the others? Making these stick diagrams, as I showed from before, results in that the energy variation of the expectation value of SZ squared actually varies like the solid line, and at the limit it reaches S equal 22. That is the maximum spin value for the system, and at the lower end it is close to S equal 9, and essentially it's difficult from such an Hamiltonian, also graphically illustrated here, to say anything about what should be the ground state. But so the formalism here says that it should be close to s equal 9, and experimentally it's found that the ground state is s equal 10. So it is there's something to it at least. Now to something completely different. Emil and Nils, PhD students here, they have been busy with synthesizing and characterizing dimers of this type. They are dimers in the sense that there are two nickel ions, and nickel ions here are the paramagnetic ones. And from susceptibility measurements, they were able to determine a J value of 24 wave numbers. And the energy level diagram is shown here in the center. It should have an S equals 0 ground state, and with an S equal 1 at 24 wave numbers. But see, if you look at the crystal structure here, there are actually two different nickel distances. There is a long distance of 8.5 angstroms, and then there is a shorter one between dimers of 7.2 angstroms. And essentially, how should you now be able to decide that the interaction you see is between these two nickels or between these two nickels? This question was raised many years ago when Kaufman collected all data which were available at that time, and then he simply made a logarithmic plot of J values versus distance. And he then took a ruler and made this line and said that this was probably an upper limit for the value of J as a function of distance. But already at that point, he noticed that there was a very, very large J value corresponding to a very large distance. And he made a drawing of the crystal structure and saw a situation similar like this one here to the right, and noticed that there, in that crystal structure also was one distance which was very much shorter. So he moved that point inside the line and all was good. And here we are actually in the same situation. Is it this distance or is it that distance? And there is actually, to our knowledge, only one method which can decide this, and that is if you try to make use of the technique of inelastic neutron scattering. See, what you do is you hit the sample, which is here, with neutrons of a very well-defined energy, and you measure the energy, the velocity of the outgoing neutrons, and you look at how much energy has been transferred to the sample. And the output, the primary output from such an experiment is shown here. And the red colors here mean a lot of neutrons, and dark colors mean no neutrons. See, most neutrons come out with exactly the same energy as they came in with, but some neutrons have lost an energy here on the ordinate, and they are horizontal lines in this diagram, meaning that these excitations are localized. So they are not, they are localized, that is within a molecule. But when you do this on a dinuclear thing on two nickels, you get interference terms, and these interference terms, they tell you immediately what distance is involved in such an excitation, because if the two centers are correlated, that is, if they are interacting, there is a one-to-one correspondence between the oscillations and the distance of the relevant ions. And this an INS spectrum of such a nickel dimer is shown here. And if you look at how this intensity of this line and of this line, how it varies with Q, which is essentially how it varies with scattering angle, is shown here. So these are the error, as a point with error bars are the raw data, and these are the computed intensities for two transitions, and they clearly say that the two centers which are giving rise to this J value are separated by 8.5 angstroms. This was actually it.